All right, so in 12.2, we went over the basics of vectors, and we talked about some operations that we could perform on them. Addition, subtraction between two vectors. We also talked about scalar multiplication, so taking a scalar or a real number, multiplying that to a vector. What we didn't talk about is if there's a way to multiply two vectors together. And it turns out there's two different ways that we cover in this class of how to take two vectors and multiply them. So two different types of products. One of those products we discuss here in 12.3 called the dot product. And you can take any two vectors of the same dimension, so two vectors in 2 space, two vectors in 3 space, two vectors in n space. It doesn't matter, and you can perform a dot product on them. In 12.4, we're going to define a different type of product which is used for a different purpose called the cross product, and those types of products only apply to vectors from R3. You can't take a cross product between two vectors in R2. They have to come from R3. But we'll get to that in 12.4. So let's introduce the dot product. We're going to do this just from the mathematical definition. We're not going to give much in the way of intuition as to why the dot product is defined the way that it is right away. We'll kind of work up to that point. So suppose you have two vectors, and we're going to use vectors in R3 here for our definition, but this applies to vectors in any size. So let A and B be these two vectors in R3 here. The dot product is the number which we denote A dot B, and that's how I'm going to read that. And it's equal to this. You notice it's the sum of the products of corresponding components in these two vectors, A1 times B1 plus A2 times B2 plus A3 times B3. Now the interesting thing about this is that we're taking two vectors and performing this product, but the result is not a vector. The result is a real number or a scalar. So that may be a little unexpected. You may expect that if you take a product of two vectors, that the result should be another vector. That will be the case with cross products, but it's not the case with dot products. Now, before we actually jump into this example, I do want to point... Actually, let's do this example, then I'll come back to this. I mentioned here the dot product is defined in a similar manner for vectors in 2 space. So if you have a dot product of two vectors in 2 space, you multiply the first component from each vector, and you multiply the second component from each vector, and you add those. Same general idea. Let's just evaluate a quick dot product. Here, we're given two vectors, u and v, and the dot product will multiply their first components, so 3 times negative 3, plus the product of their second components, 2 times 1, plus the product of their third components, negative 4 times 10. Okay? And this works out to negative 47. So again, you see that the product, the dot product specifically, of these two vectors did not turn out to be a vector. It turned out to be a real number. All right? Now, if you look at the first few exercises in the section 12.3, like homework exercises, you're going to see some expressions that it gives you involving dot products and things like that, and it's going to ask, is this expression meaningful or not? And that might be a little bit confusing, but the reason it's doing that is because it wants to call attention to the fact that you can't do some of the same things with dot products that you would have done with just regular real number multiplication. In particular, it's impossible to take a dot product like this. You can't do a dot product of 3 vectors at the same time. And why is that? Well, first of all, whether or not you realize it, you're implying parentheses in here somewhere. You're implying an order. So typically if you write u dot v dot w, if you're thinking of this as regular multiplication, you're thinking, let's do u times v, get an answer, and then do that times w, right? So really, by doing this, you're kind of implying this. But the problem is that once you take this dot product, the result of that is a scalar. And w, I should probably put these arrows here, w is a vector. So once you've done the first dot product here, now you're trying to take the dot product of a scalar with a vector. That's not defined. There's no such thing as a dot product of a scalar with a vector. So this is literally impossible. I mentioned this, one, because there's some exercises in the book that do that. But actually, I just taught linear algebra over the summer, and we use dot products in that class as well. More generally, something called an inner product. And I had some test questions where students tried to do this. They tried to take a dot product of three vectors at the same time because they thought it was proving the thing I was asking them to prove. And I had to go back and say, that's literally impossible. You can't take the dot product of three vectors all at the same time. There's no way to do that. So need to be careful with that. Now, the dot product being, a new operation that we've defined, there's a number of properties that we can try and talk about with it. 5 properties are listed here, and we're not going to go through and prove all of them just because they're fairly straightforward to prove, just kind of time consuming. I did want to do the proof of number 1 though, just because this is a really interesting property of the dot product, in that it ties the dot product to the concept of the magnitude of a vector. It turns out that if you take the dot product of any vector with itself, the result is the square of the magnitude of that vector. And to see why, let's again work with some vector in R3. And this would apply to a vector in any n-dimensional space. But if these are the components of my vector A, A1, A2, and A3, what does it look like to take the dot product of A with itself? Well, A1, A2, A3 dotted with A1, A2, A3. I'm multiplying A1 times A1, that's A1 squared. And then similar for the other components, A2 squared, A3 squared, and I add those up. This, though, looks just like the radicand of the formula that I use to compute the magnitude of A. So if I do a little unsimplifying on this, if I put a radical, a square root around it, and then I square that to sort of undo the square root, I can see that the square root inside here is really just the magnitude of A. And that gives me what I'm looking for, magnitude of A squared. Okay? So interestingly, already, the dot product, which seemed to be defined in sort of an arbitrary, it feels like a meaningless thing to define the dot product the way that we did, but it already has a connection to something that we know we want to be able to compute with vectors, magnitudes. And it has a lot more value than just that, as we're going to see. So here's the next and probably more useful property of the dot products. So if you have two vectors, let's say, let's call them A and B like this, we can talk about the angle between those two vectors. Remember, vectors can be anywhere in space, but if we want to talk about the angle between them, we're going to think of the two vectors as having the same initial point like this. And we're going to think of the angle between them as the smallest angle between them. What I mean by that is if you have two vectors in the plane, there's technically two angles between them that we could be talking about. We could be talking about this theta right here, or we could be talking about this much larger angle out here. This is what's called a reflex angle. We're implicitly assuming that when we talk about theta, we're talking about this angle right here. And you should be able to see that if that's what we mean by theta, then theta can only take on values between 0 and 180 degrees, or 0 and pi. Because otherwise, if A goes, if we rotate A past 180 degrees, now the smallest angle would be down here instead of up here. But anyways, keeping that in mind, it turns out that if theta is the angle between the two vectors A and B, then the dot product is equal to the product of the magnitudes of A and B times the cosine of that angle. Now this seems completely different than how we define the dot product up here, and we're going to prove on the next page that the dot product we defined at the beginning of this section is actually the same thing as this. They both give you the same result. It's worth noting that a lot of times engineers, physicists, if you're an engineering student, it's pretty common to actually define the dot product this way. So in engineering textbooks, oftentimes, this is what you're given as the definition for the dot product. And then you sort of show that the other definition that we've been working with is a consequence of this. But we can define it either way because the two definitions turn out to be equivalent. So let's show that we can use this definition that is consistent with what we define to be the dot product. What we're going to do is take the vectors a and b that I drew on the other page, and notice there's the angle theta between them. I'm going to make them position vectors so that their common initial point is the origin. And then in section 12.2, we showed that the difference between two vectors can be thought of as kind of the other side of this triangle here. So if you have the two vectors sharing this initial point, then a minus b is going to be a vector that connects their terminal points but points towards the first vector in that difference, towards a. Now the direction that it points isn't going to matter for this proof because we're strictly going to be working with the magnitudes of these three vectors here. But the key thing is that a minus b completes this little triangle with these vectors. Now, because it's a triangle, and because we're specifying one of its angles right here, that opens us up to some trigonometry that we can use. In particular, in trig, you have something called the law of cosines. And we're not reviewing the law of cosines here, we're just going to use it. So if you don't remember how that works, it'd be worth looking that up and just kind of refreshing yourself on it. But basically, law of cosines says if I take the side that's opposite the angle that I'm using and square its length, so notice we're using some points here, O for origin, A and B for these points, so that the line segment AB, its length is the same thing as the magnitude of this vector, so that's why we're using this notation. But that length squared should equal the sum of the squares of the other two lengths of the triangle, here and here, minus 2 times the product of the lengths of those two sides times the cosine of this angle. That's something that you prove in a trigonometry class, and usually it looks like a squared equals b squared plus c squared minus 2bc cosine of theta. We're just using different labels for things here. Okay. Now this proof is cut right out of your book, so I'm going to jump past this part right here. What we're doing here is we're replacing these this notation with line segments with the magnitudes of the vectors that represent those line segments. So really, this is the same thing as saying the magnitude of a minus b squared minus the magnitude of a squared plus magnitude of b squared plus yada, 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 right? Now, we're going to use a few properties of the dot product to write this and simplify it a little bit. So specifically focusing on the left-hand side, notice we have the magnitude of some vector squared. But that property that we proved with dot products says that the magnitude of a vector squared is equal to the dot product of that vector with itself. Okay, so I can rewrite that magnitude of a minus b squared as a minus b dot a minus b. Now, some of the other properties that we didn't really spend time talking over, but we looked at, of the dot product allow us to perform a dot product like this. This makes you think of FOIL from algebra, you know, first, inside, outside, last, the way that we multiply two binomials. And it turns out that even though this is not the same thing as real number multiplication, because dot products have the distributive property and they have the commutative property of multiplication, we can multiply this out in a similar manner. So we get a dot a from here minus a dot b, because that's a dotted with a negative b, you can think of it that way, minus b dot a plus b dot b. The a dot b and the b dot a are the same thing because of the commutative property, and so we can combine them, and we get this. Magnitude of a squared minus 2 times a dot b plus the magnitude of b squared. Okay, so basically what we're doing is we're taking this and replacing the left-hand side of that equation up there with this new expression. And that's where this becomes this slightly more complicated looking equation. But the benefit of this is that now we can cancel a squared, magnitude of a squared from both sides, cancel magnitude of b squared from both sides, and if you look at what's left, negative 2a dot b here, negative 2 magnitude of a, magnitude of b cosine of theta. Cancel the negative 2's from both sides, because remember, both sides of this equation are just real numbers. That's what the dot product gives you in all of this. That's just real number multiplication right there. Dividing the negative 2 gives me that result that we were looking for. Okay, A dot B is equal to the magnitude of A, magnitude of B, cosine of theta. There are some cases where, in fact, the last example that we do in this section, there's cases where we want to evaluate the dot product this way because we may not know the component form for these vectors. That's entirely possible. We may be given two vectors that are described in a different way so that maybe we know the angle between them and maybe we know their magnitudes, but we're never told their components. And so we don't have a choice. We have to use this technique for doing a dot product since we can't do the component-wise definition. Now notice here, if I wanted to solve for cosine of theta by dividing both sides by magnitude of A times magnitude of B, I get this little formula right here. And what's the purpose of this little formula? Well, if I know A and B in component form, then I can compute A dot B using our first definition. I could find the magnitudes of those vectors using the formula we talked about in the previous section. And I get that the cosine of the angle between them is that number. This gives me a technique for finding the angle between two vectors. So if I don't already know that angle, I can now find it. Find the angle between these vectors here. U equals 4, 0, negative 2. V equals negative 2, 5, 1. So I'm going to use this formula. Cosine of our angle between them, which I'm calling theta, is equal to the dot product of those two vectors, 4, 0, negative 2, dotted with negative 2, 5, 1, divided by... Now... We've gone over the formula for finding magnitudes of vectors already, and it's just arithmetic. So oftentimes I'm going to do that mentally. And remember, what you're doing is you're taking the square root of the sum of the squares of these components. So 4 squared is 16. 0 doesn't contribute anything. Negative 2 squared would be 4. 16 plus 4 is 20. So I got root 20 right there. And yeah, I can simplify that radical, but I'm going to wait before doing that. Here, same thing. I need the magnitude of my second vector. That's like this right here. That's going to be 4 plus 1 is 5 plus 25 would be 30. So that's root 30. Okay. Now this, if I perform this dot product and if I multiply these radicals, there's some simplifying that happens there. But after all of that, what I end up with is negative 1 over root 6. Okay. Now that's not my answer, right? That's the cosine of the angle between these two vectors. But if I were to take an inverse cosine of both sides, theta is equal to the inverse cosine of negative 1 over root 6. And if I want my answer in degrees, for example, I'd plug that into a calculator. What did I end up getting for that one? It's approximately 114.09 degrees. Okay, that's pretty convenient because it's, you know, especially because we're working with vectors in 3 space, trying to find the angle between them is a practical thing that we might need to do for a number of different applications. But it might seem like a tricky problem without a technique like this. So we'll be using that more in some upcoming work that we do. Okay, whoops. So next we're going to define a term that you might be familiar with, orthogonal. A synonym for orthogonal is perpendicular. So we say that any two vectors are orthogonal, or we could also use the term perpendicular if the angle between them is a 90-degree angle. However, going back to the definition of a dot product, specifically that second definition that we came up with, this one, if there's a 90-degree angle between two vectors, then their dot product, which is equal to the product of the magnitudes times the cosine of the angle between them, that angle between them would be 90 degrees. But cosine of 90 degrees is 0, so this whole expression goes to 0. And what this does is it gives us a technique for showing whether or not two vectors are orthogonal. All we have to do is take their dot product and see whether or not it's 0, which is very easy to do. And it's a convenient thing a convenient tool, because you're going to see as we progress through this course, we oftentimes want to know whether or not two vectors are orthogonal. There's a number of benefits to that. So here in this example, we want to prove that the standard basis vectors whether in 2 space or 3 space, are all orthogonal to each other. So I'm only going to worry about 3 space right now. That means I have 3 things to check. I want to see if I and j are orthogonal to each other. I want to see if I and k are orthogonal, and I want to see if j and k. And what this reduces to is just checking to see if the dot products of each of those pairs of vectors turns out to be 0. Well, I is 1, 0, 0, and j is 0, 1, 0. Okay, but that's equal to 1 times 0 plus 0 times 1 plus 0 times 0, which is of course equal to 0. So I and j are definitely orthogonal to each other. These two are going to be really, really similar. So you can fill in the blanks there, but it's very easy to see that the dot products of all of those would be 0. And that should be obvious from when we looked at a picture of those standard basis vectors. Remember, they looked like this. You know, I was here, j was here, k was here, and because they coincided with the axes, we for sure had right angles in all of these, between all of these angles, or vectors right here. So this just confirms it using that technique, using the dot product technique. But let's dig into this a little bit more. So understanding the dot product as relating to the angle between two vectors, what in a more general sense does the dot product of two vectors tell us about those two vectors and the way that they're related to each other? Well, one interpretation is that the dot product can be kind of a measure of how closely two vectors are to pointing in the same direction. And actually, I'm looking at my time here. I'm gonna go through this explanation in the next video.